This is chapter 3.5, exercises 39 through 50. This set of exercises in section 3.5 has to do with using logarithmic relations by factors of 10. In fact, in problems, this set here, 39 through 44, determine how many orders of magnitude the quantities differ. A $100 bill and a dime. Well, an order of magnitude is something that is used a lot of times in regular language as a non-literal type expression. For example, say, well, something is a order of magnitude greater than that. Well, the literal meaning is an order of magnitude is a value multiplied by a factor of 10. So if I do 1 hour of work and someone else works 10 hours, that person did a 1 greater order of magnitude than I did in working. Well, here we have between a $100 bill and a dime. What we have is different units. We have a dime. Well, we have to know how many dimes there are in a $100 bill. So what we can do is we can change this dime, and a dime is equal to $0.1. All right. So an order of magnitude, we'll be able to determine that by how many times do we multiply it by 10 to get to the next value. So if we take this dime of 0.1 and multiply it by 10, we get a dime times 10 is $1. And so that's going to be 1 order of magnitude. And if we take this $1 and multiply that $1 by 10, we get $10. So we've gone to our second order of magnitude. I'll put 2 here for that. And then finally, if we take this $10 and multiply that $10 by a factor of 10, we get $100. So that's our third. So we multiplied this dime by 10 3 times. So if we just take this, one way to look at it, if we take this 0.1 times 10 to the power of 3, we're going to get $100. So I'm going to put OM for an abbreviation of order of magnitude, in this case 3. And that is our answer for problem 39. Next on our problem is problem 41. And exercises 39 to 44 determine how many orders of magnitude. An earthquake rated 7 on a Richter scale and one rated 5.5. We have to have an understanding here that a Richter scale is a logarithmic scale. And so what we have is our order of magnitude is going to be determined by taking the Richter scale measure of 7 and subtracting from it 5.5 to get 1.5. And this consists of our order of magnitude, 1.5. But in order to do this, we had to understand that this Richter scale is a logarithmic scale, and we could actually subtract and have that be our order of magnitude. So we had to have some level of understanding to do this. 42, I'm not going to do this, but it's again a pH scale for acidity and alkalinity is a logarithmic scale. Okay, 43, the sound intensities of a riveter at 95 decibels and ordinary conversation at 65 decibels. So this one's a little different. If we take our difference and take 95 and subtract from it 65, we get 30. Well, what happens for the decibel scale is like this. Your decibel measurement is 10 times the log of the ratio logarithm of the sound intensity I over I sub 0. And I sub 0 is 10 to the negative 12 power watts per meter squared. Okay, and then we find it. But you see, for decibels, you multiply by 10. So we have to take this 30 and divide it by 10 to get our orders of magnitude, which is 3. So for this one also, as in problem number 39, our order of magnitude is 3. And we had to divide those by 10 to figure that out. Next, comparing earthquakes. How many more times severe was the 1978 Mexico City earthquake, R equals 7.9, and the 1994 Los Angeles earthquake, R equals 6.6? Basically, the formula for earthquakes, the way it works out is this. If you have an earthquake, we'll call it R sub 1. If you take the shaking amplitude, or not the shaking amplitude, the Richter scale difference, it's going to be the log of some shaking amplitude over T minus the log, and that's log base 10, of the shaking amplitude of the second earthquake over T. And we combine these logarithms, and using the rules of logarithms, we can take this on the left is equal to log of, we have in the numerator a sub 1 over t, and the denominator a sub 2 over t. And again, on the right side we have R1 minus R2. And so when we work this out, I'm going to work this out on the left. If we have a sub 1 over t, we can divide by a sub 2 over t by taking the reciprocal, multiplying by the reciprocal of the denominator. So instead of dividing by a sub 2 over t, we can multiply by t over a sub 2. And so t over t will cancel each other, and what we have left is the log of the ratio of a sub 1 to a sub 2 equals R sub 1 minus R sub 2, the two earthquakes. So in this case, what we have is, we know that R sub 1 minus R sub 2, we define R sub 1 to be 7.9, and R sub 2 to be the second earthquake, 6.6, is going to be equal to the log of that ratio. A sub 1 over A sub 2, and that's going to equal 1.3. So I'm going to come over here to the right a little bit up. So we have the log meaning log base 10, which I write here, of our ratio of a sub 1 over a sub 2 is equal to 1.3. Now, can we write this as an exponential equation? Yes, we can. The base of the logarithm becomes the base of the exponent. So we have 10 to the power of 1.3 is equal to the ratio of a to 1, a sub 1 to a sub 2. And so we have 10 to the power of 1.3. So you go to our calculator, we put in 10 to the power of 1.3, and we get 19.95. So we will just summarize this. We will say about 20 times greater. So that's going to be our answer for problem 45. Next, problem 47. The pH of carbonated water is 3.9. The pH of household ammonia is 11.9. What are their hydrogen ion concentrations? I want to see if I can create a little more room here. Okay, what we have here is our formula is given right here. pH is equal to negative log of the concentration of the hydrogen ion. So, and for carbonated water, we have 3.9 is equal to negative log of what that concentration is, which I write like this. And so we can go ahead and divide by negative 1. So if we have negative 3.9 is equal to the log, and I'm going to go ahead for abbreviation's sake, make this hydrogen concentration X, and that's going to be log base 10. So continuing to the right, to change this into a logarithmic, an exponential equation, we have 10 to the power of negative 3.9 is equal to X. And that's going to be our concentration for carbonated water, pH concentration. So we go 10 to the power of negative 3.9, and we get 0.000126. Let me just write this out. And this is going to be the same as 10 to the, excuse me, not 10, but rather 1.26 times 10 to the power of how many decimal places? 1, 2, 3, 4. 10 to the negative 4 power. So this is going to be our this is going to be carbonated water pH. That's going to be the hydrogen ion concentration. So carbonated water. And next, for this household ammonia, we're going to have very similarly I'll put negative 11.9 equals log x. I'll put log base 10x here. And rewriting this as an exponential function, we have 10 to the power of negative 11.9 is equal to x. And going to our calculator, we have 10 to the power of negative 11.9. So we get 1.26 times 10 to the power of negative 12 here in scientific notation. .26 times 10 to the negative 12. And this is going to be our concentration of household ammonia. So I'm going to put ammonia. So really this is part A worked out. Now part B, how many times greater is hydrogen ion concentration of the carbonated water than that of ammonia? So to do that, I'm going to just put B over here. We take this 1.26 times 10 to the power of negative 4 over 1.26 times 10 to the power of negative 12. And we have 1.26 over 1.26 canceled equal 1. So we have 10 to the negative 4th divided by 10 to the negative 12th, which is going to be 10 to the negative 4 minus negative 12, which equals 10 to the power of negative 4 plus 12, which equals 10 to the 8th. Now 10 to the 8th is, I think that's 100 million. So it's going to be 10 to the 8th times greater. So that's going to be our answer to part B. And finally, part C. By how many orders of magnitude do the concentrations differ? Well, that's going to be easy because we have 10 to the power of 8. So our order of magnitude between these two concentrations is going to be that power of 10, which is 8. So let's go ahead and write this down. Okay, good. Similar problem, 48. 49. Newton's law of cooling. A cup of coffee is cooled from 92 degrees centigrade to 50 degrees centigrade after 12 minutes in a room with a temperature of 22 degrees C. How long will it take to cool to 30 degrees centigrade or Celsius? That's what they call it, Celsius now. Make this a little smaller, get a little more room. Okay, we're given the formula. This is one that will take some work because what we have to do is use this cooling we've done here after 12 minutes with the time to go and find the value of K. And then having found K, we plug K back into the original equation to find what our final temperature is. So we'll just set this up. We have the time we cooled to 50 degrees Celsius is equal to the temperature of our medium, which is 22 degrees Celsius, plus we have our initial temperature. We are given 92 degrees Celsius, minus our medium temperature, which is 22, times E, which is Euler's number, to the power of negative K, and T we have is 12 minutes. So that's our basic equation we're going to work out. And solving for K, that's going to be it. So if we subtract 22 from both sides of this equation, we get 50 minus 22 is 28. So we have 28 equals, and we can take this 92 minus 22, and I think that's 70. So we rewrite that as 70. And we have e to the negative k times 12. And if we divide by 70, both sides, we have 28 70ths. It can be simplified, equals e to the, I'll put negative 12k right here. And then we can change this into a logarithmic, or a natural log, which is log base e. And to do this, we're going to take our base of our logarithm, our base of our exponent becomes the base of logarithm. So we have log base e, which is ln, of 28 70ths is equal to negative 12k. And now dividing both sides of this equation by negative 12, you have cancellation here, so we have k isolated. I'm going to go ahead and come up to the right and up a little bit here. So I'm going to say k is equal to, this log base e is just ln, we'll call that ln now, of, I'll say 28 70ths, and all that divided by negative 12. So we're going to get our value of k. Let's do that in the calculator. We have ln, we press control ln, and we have 28 over 70, and we divide this by negative 12, and we get 0.076358. So now we have, that is our value of k. So now we can go back and figure out how long the thing will take to cool to 30 degrees Celsius. And I'm going to write out that equation. So our final temperature is going to be 30, and it's going to be equal to our temperature of our medium, which is still going to be 22 plus, and we have our starting temperature is the same as in the previous. We had 92 minus 22 degrees Celsius, and we have e to the negative k. Well, that's going to be 0.076358, and that's going to be T, which we do not know. Okay, and we can go through the same process similar to we did this left side in the blue, but I'm going to just go to numerical solve, which is a great feature in the TI Inspire calculator, which can help you undo things like this. Okay, if we go to the calculator and we do that, to do that we go to menu, algebra, numerical solve, So we have, looking for 30 degrees is equal to, we have our let's look up here. We have our medium, okay? Our medium, which is 22, plus we have 92 minus 22 times e to the power of negative 0.07. Remember what they are. 0.7635. Yeah, it's right here above. 6358 times, we'll say x. And then I think that's going to be all we need. We press comma x, and it should give us our value here. So we get 28.4. So that's going to be t is equal to about 28.4 minutes. So quite a little process there. Anyway, good luck on these even number problems. And as always, thanks for viewing.